Okay, hi guys. We're going to continue to see the applications of the second derivative. Yesterday we saw when the definition of concavity, and we saw what is concave upwards and what is concave downwards, right? So today we're going to see one of the last topics of the second derivative, that is inflection points. Okay, so what is an inflection point? Is a point where the type of growth of our function changes. For example, as we can see in this part, we have a function that is concave upwards, and suddenly in this point it changed to be concave downwards, right? This is like happy face and it turns to a sad face, right? So in this point, in this inflection point, our function, the growth of our function is going to change, right? Here is increasing, but increasing very low, very high, really high, really fast, and then it is still increasing, but increasing low. Same here. First, it is increasing low, and then it is increasing but very high, right? We have an inflection point here, and then in the final example, we have a similar example that it is increasing very high and then increasing very low. These points where the function changes, or our increase on the function changes, are called inflection points. So we're going to see the definition of inflection point. Okay, if CFC, okay, a point CFC is an inflection point of the graphic of f, this is f, then the second derivative evaluated in C is equal to 0, or the second derivative evaluated in C does not exist, right? It's similar to finding the critical numbers, but with the second derivative, okay? So before we move forward, let's do a little example of how to find inflection points, and then we will continue with the intuition behind the inflection points, all right? So, an example: determine the inflection points and analyze the concavity of this function, x to the 4th power minus 4x to the 3rd power, alright? So, what we just saw is that an inflection point exists when the second derivative is equal to 0, or when the second derivative does not exist, right? So, what do? Take out the second derivative of fx, right? Fx is equal to this, we can rewrite it. So the first derivative will be, we take down the 4, 4 minus 1 is 3, minus 4, well, let me put 12, x, 3 minus 2, minus 1 is 2, right? This is the first derivative. So the second derivative would be 12x squared minus 24x, right? So we have to do this equal to 0 to find the inflection points. Equal to 0 would be, we can factorize a 12x actually, and we get this. Are you agree with me? Okay, so when does this equation become 0? It becomes 0 when this part is equal to 0, or when this part is equal to 0. Alright? So 12x equal to 0, or ix minus 2 equal to 0. Then we can see that our first root, the root of our second derivative, is 1, and our second root of the second derivative, yes, is 2, right? So these two must be the inflection points, right? What do we do with them? As we saw in other exercises, we can't make intervals with them. Alright? So let me erase this. I have my eraser, but alright. Okay, so the intervals 0 and 2, right? So minus infinity to 2, that is 1, no, to 0. The second one would be 0 to 2, and the third one 2 to infinity, right? So we have to evaluate values that are in each interval. So we have the intervals. We have to choose a number between the intervals, that is in the interval. So for the first case, we pick -1. We have to pick easy numbers, right? -1. In the second, we will pick 1 positive, and in the third, 3. And these numbers, we're going to evaluate them in the second derivative. Okay? We only want to know if the second derivative is positive or if it is negative. Okay? Okay. So the first number, 12 to -1 squared minus 24 minus 1 minus per minus is positive. This becomes positive. So f of -1 must be greater than 0. Right? Are you agree with that? Okay. So the second number, 1 positive, is 1 to square minus 24 multiplied by 1. 12 multiplied by 1 minus 24, that is negative. You can see it? Okay. And the third example, if you do the math with your calculator, you will get that it is positive. Okay? The second derivative. I'm sorry for that. Okay. So what can we conclude with this information? Here, that here is positive, here is negative, here is positive. So this is happy, concave upwards. This is sad, concave downwards. And this is happy. Okay? Concave upwards. So as you can see, in the inflection point 0, it was upwards. In 0, it becomes backwards. And again, in 2, it becomes upwards. Okay? We're going to do more examples of this, and I will give you some homework to do to analyze it with more time. Okay? Okay, so yesterday we saw this example, right? Let me move this a little bit. All right. Yesterday we saw this. The first, we have a function fx. The derivative will look like this. This might be a cubic expression, this might be a quadratic expression, and this might be a linear expression, right? So, what did we saw? That in the critical points, we will have maybe a maximum or a minimum, we don't know, when in the critical points when the first derivative is equal to 0 or it does not exist, right? And what else do we know? We know that when the first derivative is greater than 0, our function increases. When it is lower than 0, our function decreases. And when it is greater than 0, our function increases, right? We know that. So, what information we can get from our second derivative? Okay, that is the question we're analyzing. So, let's see. We know that in the critical points, in these points, there will be a maximum or a minimum. We don't know yet what it will be. Okay, we just know that it will be the top or the bottom of the function, right? So it can be a maximum or a minimum. But let's see something interesting. When the first derivative, the second derivative, I mean, is negative, when the second derivative is negative, we have a maximum, max. When the second derivative is negative, then that point, let's say this is C. C is max. Okay? Okay, I'm sorry. Okay. And when the second derivative is positive, we will have a minimum. Okay? I will write this down. Just take a look at that. Okay? When the second derivative is negative, we will have a maximum point. And when it is positive, we will have a minimum point. Okay? Okay, very well. So, when our second function is positive, when we have a happy face, a function concave upwards, we will have a minimum point, which makes sense, right? The minimum point. And when it is negative, the second derivative, when we have concave downwards, then we will have a maximum point, okay, in our original function, right? So let's do an example. So what are the steps? Okay, let's say we have a function fx in the closed interval ab. Okay, first step, determine the critical numbers. How do we do that? Evaluating or making the first derivative equal to 0. Or I am missing this part of the definition, right? But most of the times we will have just to get this, okay? Second, evaluate these critical numbers in the second derivative. If the second derivative in that number is positive, then that C will be a minimum point. And if it is negative, then C will be a maximum point. Okay? So we're going to do